Ah, perfect. Yeah, so here we go.
Right. It's okay.
Yeah, it says the live stream was starting at 3:15 on YouTube.
Oh, that must have been the OBS one that I did.
Oh, is there a new one? Here, there we go. Oh, okay, there. All right, I've got the live stream up and everything now. Perfect, so I can monitor that. Okay, so it's officially 3:30. So for everyone who is in the Zoom call and on YouTube, we're just going to give 5 minutes as people trickle into both the Zoom call itself and the live stream. And then, yeah, in about 4 or 5 minutes, Yilda, I'll give the floor to you and you get to tell us about your research. Super excited.
Sounds good. Thank you.
And yes, we got some people coming in on the live stream now. Perfect. Right, for those who have just joined the YouTube live stream watch, we're just giving a few more minutes for people to join. And then around 3:35, we're going to kickstart it off. All right, we're going to give about 1 more minute for people to pop in on either Zoom or YouTube, and then we'll get it started. All right, so I think we are good to now start off the presentation. So welcome everyone to this month's HQP seminar. Today we are joined by Yilda. So Yilda is going to talk to us a little bit more about astroparticle theory, specifically what we should look for if we want to consider dark matter as a composite state. So Yilda is going to discuss what a composite state dark matter looks like, as well as how this might manifests inside things like our detectors and how we can search for it. So Yilda, I'll give it away to you.
Thank you, Ryan. And hi, everyone. My name is Yilda. I'm a PhD student at Queen's University in the High Energy Astroparticle Theory group. And I'll talk to you a little bit about new searches for super heavy composite dark matter. So I'll spoil basically all the key points of today's seminar right now. So what I'm trying to get across is heavy composite dark matter can form in the early universe, and so exists today similar to nuclei in the standard model as a composite state rather than free-floating individual dark matter particles. And we'll see that because of the phenomenology of these composites, you can have multiple scatters in a detector if one of these composites passes through. So I'll talk about that in a few different scattering regimes, one of which is the extremely loosely bound regime, so where the binding energy is really small for these composites. And we'll see that they could disassemble completely as they pass through the Earth, and you end up with a cloud of disassembled constituents passing through your detector, and that's a different multi-scattering signature. I'll also talk a little bit about astrophysical probes of super heavy dark matter. And specifically how it can cause extra type 1a supernovae from disrupting white dwarfs and change galaxy evolution that way, as well as a different detection mechanism using ancient minerals. So these are sort of the spoilery outline of what I'll talk about today. Hopefully we can get through all of that. We'll see. So first I want to start with what is this ultra heavy dark matter regime? So dark matter, we believe exists, but we don't have a handle on how massive it is. So if dark matter is a particle, it could live anywhere from the ultra light dark matter regime with axions up to a more standard, WIMP image, which a lot of detectors look for here in Canada. And as you get to larger masses, you can have dark matter being a composite state, as I'll focus on, or even as massive as a sun, it could be a primordial black hole, etc. So what I consider the ultra heavy dark matter limit is anything that's much heavier than the WIMP, so much heavier than like 100 TeV. So for scale, 1 proton is like 1 GeV of mass. 10,000 protons and higher. And we'll find that a lot of these models have to be composite. But first, before we get into the nitty-gritty of that, I want to talk about why heavy dark matter is interesting to look for. So when we search for dark matter in a direct detection experiment, the primary one of the primary constraints that we have is the flux. So how much dark matter passes through your detector over the lifetime of your experiment. And that's not something you can really control, right? That depends on the density of the dark matter around the Earth. And we have a good handle on what the density of dark matter is in the Earth neighborhood and throughout the galaxy. But since we don't know the mass of an individual particle, we don't know necessarily the number of dark matter particles passing through the detector. So if you fix the density, you increase the mass, you end up with a lower flux. So on the left-hand side here, I'm showing a standard WIMP mass versus cross-section diagram of exclusion limits from different experiments. So anything essentially above a given line from an experiment is excluded. They would have seen it if dark matter was in this region. That's the idea. And you see as you get higher and higher in mass, you're less and less sensitive, essentially. You're less and less sensitive because you have fewer dark matter particles passing through your detector. And what this means is that if the dark matter is really heavy, it's not as constrained, so you can have a really high cross-section. The cross-section being how much can it interact with the standard model stuff in your detector how many interactions can there be. So you have a lower flux, fewer dark matter particles, but each one of those could scatter a lot, potentially. And so that leads to the potential signature of multiple scatters in the detector. So one particle goes through, there's my dark matter particle in pink, and then it interacts multiple times in my beautifully drawn liquid argon experiment or whatever that may be. And there's a few different formation models in the literature, many of them, discussing how you can form this heavy dark matter. In this talk, I'll mostly focus on early universe assembly, which has been studied by various groups, where essentially you just have individual dark matter particles with some sort of attractive force between them, and then clumping together to make essentially dark nuclei or dark clumps of dark matter, and that's what's hanging around us today. So I'll talk a little bit more about this production in the early universe. So many of you may be familiar with the WIMP freeze-out picture. Essentially, you have a bunch of dark matter and anti-dark matter, let's say, annihilating in the early universe. And so as the universe expands and time goes on, you end up with a certain amount of density remaining once your annihilations are no longer efficient, and that's the amount of dark matter that's left today. And the great thing about WIMPs and what we call the WIMP miracle is that the cross-section you expect, like the cross-section you expect for the annihilation to happen, to give the current dark matter amount that we see, corresponds with the weak scale cross-section. So something we can search for with direct detection experiments. But as you increase the mass of the dark matter, you end up hitting an upper bound, essentially on how likely your annihilations, how efficient your annihilations can be. So your annihilation cross-section has an upper bound that depends on the mass. And you need a sufficient amount of your dark matter to annihilate away in order to get the amount that we actually do see in the universe. So that sets like an upper limit of 10 to the 5 GeV on the standard freeze-out mechanism of getting today's relic abundance of dark matter. But if you want to look at dark matter that's a lot heavier than this, which I do, you can look at different mechanisms that aren't the same freeze-out mechanism. One way that many people have looked at is squeeze out from some sort of phase transition. I won't go into that too much, but essentially you could have really dense pockets of a false vacuum where your dark matter is really tightly packed and can annihilate pretty efficiently and give you the right amount of dark matter left. Or you could have dark matter form and make composites, essentially. And in that case, your individual dark matter particles are perhaps not that massive, but because they can make really large states, your entire composite is really heavy. And so this is what this can look like in the models of composite dark matter that we study at Queen's. You start out with some dark asymmetric fermionic dark matter. And asymmetric essentially is there's some amount of dark matter, some amount of the anti-dark matter, and these annihilate, but there's some amount of asymmetry between how much there is of each. So the leftover amount gives you the relic abundance today. So similarly to the baryon anti-baryon asymmetry in the early universe in the standard model. And then if these particles are hanging around, perhaps they form nucleons, but we won't go into that too much. But if there is a attractive force between these dark matter particles, this attractive force is going to allow them to clump essentially and form composites. Similarly to the strong force binding nuclei together in the standard model. The key difference is that in the dark sector, you don't have to have a repulsive force. Like in the standard model, your nuclei have protons, neutrons. The protons are repulsive, and so that sets like an upper bound of how many nucleons you can pack in a nucleus. But in the dark sector, this is not necessary. So if you don't have such a bottleneck, you can form really large composite states. And I'm talking about number of constituents that could be like 10 to the 13, 10 to the 20. And that's all kind of set by how strong this interaction, this like attractive force between the different particles is. So essentially, when the universe temperature drops below the confinement scale, you end up being able to form these composites. Essentially, if your universe is not hot enough to break these apart, because the particles have enough energy to break apart the composites, then they start clumping. And based on these early universe dynamics, you can predict how many dark nuclei you expect in your composite state. And a lot of the important scalings that we'll see are vital for direct detection end up coming from this. So you have dark matter particles plus the force. If you consider how much like the interconstituent spacing is, so the stronger the force, the more tightly bound this composite is. The spacing between different constituents is smaller. So that kind of sets the binding energy, also the size of the actual extent of the clump, the number of constituents, etc. Well, let's tie this back to direct detection for a second. I told you already that because heavy dark matter is much less constrained, it can have a higher cross section, and it's still fine that we haven't observed it because the flux is so low, the number of particles is so low. Different experiments have done already different direct detection searches, specifically looking for multi-scattering in a detector, where one really heavy particle comes in and hits a bunch of times all in a row along its path in a detector. So here I'm just showing some exclusions from Deep 3600, from Xenon 1 ton, and from Lux Zeppelin. And these are dedicated multi-scattering searches. You can't simply rescale the WIMP exclusions because those are looking for individual events, whereas this is looking for really correlated scattering within like the path of the dark matter. And so these have been done for like a general model, assuming a certain scaling of how does the cross-section of the dark matter change as I'm changing the mass of the dark matter. And so this equation here on the bottom left is the differential cross-section between a nucleus of mass A and a dark matter state D. And we can see that the way that this scales with mass depends on the reduced mass, which is the mu terms in the mu squared terms. And if the mass of the dark matter is a lot bigger than the mass of your target, this ends up scaling as a to the fourth. So it scales as whatever your target essentially mass number is to the fourth. And so that's great because that's a bit of a extra boost to your cross section, which is always helpful for when you're looking for these kinds of things. So this is an assumption you can make if you're looking to constrain essentially a broad spectrum of models using a direct detection search. Except it is not always that easy. One paper a few years ago showed that there's an upper bound on this cross section. You can't just it can't just increase as much as you want. The reason for this is that at some point you're limited by the geometric size of your target, essentially. You can't like have a cross section that's larger than the size of the target, essentially. So this upper bound can disrupt this sort of search. So the question is, can this heavy dark matter actually scatter with the a to the fourth scaling, or a scatter with a scaling that allows the multi-scattering? So that was the impetus for looking at composite dark matter in the loosely bound regime. So what do I mean by loosely bound? This has to do with the binding energy of the particle of the composites. So these are held together by a force, an attractive force, they're clumping. And depending on the strength of that, you need a different amount of energy, right, to to dissociate it. And therefore, the stronger something is bound, the smaller, the more tightly bound it is. Its physical extent is a bit different. So, for instance, you could have composite dark matter that is still point-like. So it's so tightly bound that from the outside, from the perspective of a standard model nucleus, which is what I'm showing in the yellow circles, the composite structure itself is irrelevant. So it doesn't matter that it's a composite state. That's the tightly bound regime, which is shown here on the plot in blue. And that corresponds to really small interconstituent spacing. So you can think like if something is really tightly bound, everything is squished all together so much more, the spacing between things is smaller. Then if you increase that interconstituent spacing, at some point your dark matter composite is going to have an extent, like an actual size. And that means that it'll have a form factor similar to nuclear form factors. At this point, you have to start considering the composite structure, and that changes how you calculate your scattering probabilities. Finally, if you have it super loosely bound, the composite state is so large compared to the standard model state or the momentum transfer that primarily you're scattering not coherently with the whole state, but with individual constituents inside. And this, again, has a different scaling. So what does this do for actual multi-scattering searches? So on the left-hand side, I'm showing the number of scatters you expect in log scale in the color plot for varying mass of the composite on the x-axis and on the y-axis, the cross-section. The black outline is the deep 3600 contour of their multi-scatter search for the scaling that I was talking to you about before, the a to the fourth scaling. So this is what you would expect from a to the fourth scaling. You can see that at higher cross sections, you can get like 10 to the 6 scatters from dark matter multi-scattering. So multi-scatterings can happen. Then in the middle plot is the same axes, but what I'm showing is the point-like case. So where the composite is so tightly bound that the structure inside is irrelevant. And this is bounded by the geometric limit on the cross-section. Because you have an upper bound on the cross-section of about 10 to the minus 38 centimeters squared, you see that that whole region has like fewer than 10 scatters, which really suppresses the likelihood of the multi-scattering. And so you can say, is this bounded region actually, like, is this constraint actually valid here, right? But it turns out if you consider composites that are scattering primarily through the constituents, because they're so loosely bound, you can recover the behavior that is expected from the a to the fourth scaling. So on the very right here, you can see that the scattering rates are as one might expect. So this is useful in order to know which composite dark matter models can you constrain with multi-scattering searches, which ones evade the geometric upper limit on the cross-section that kind of stops multi-scattering from happening. For the sake of time, I won't go too much into dark matter scattering with electrons. I could go back to it if there ends up being time, but the idea is that if you have this same composite state hitting an electron that is bound to an atom, if that electron doesn't actually leave its orbital but still gets the recoil, that can induce a recoil of the whole atom. And these are usually very low energy recoils. But if you have a large composite state that could interact with multiple atoms, essentially, you could get a really large number of these small recoils. Now, one part of this plot that I didn't talk about when I was talking about the scattering parameter space is the dark matter disassembly region up here in red, which, as you can see, is at the very high end of the interconstituent spacing. So these are the most loosely bound composites. And what's happening here is that the composites are so loosely bound that when a standard model nucleus interacts and scatters with a constituent inside the dark matter composite, it imparts enough energy to actually kick that constituent out of the composite completely. This is the disassembly regime. So that's what's going on here. You can see the interaction occurs, and then one of the constituents is kicked out of the composite with some angle, like reflection angle from the scattering. And so what we looked at is what happens if a super loosely bound clump of dark matter, composite dark matter, passes through the Earth before it gets to a detector. If it passes through the Earth, it will still interact with the Earth itself, and that can dissociate the composite completely and break it into pieces if you have sufficient successive scatters. So I'm showing you here a picture of a dark matter composite hitting the Earth with some entry angle relative to the Earth's surface. And then as it goes through, each constituent might be kicked out of the composite state. And then as this, each constituent will then follow essentially its own path through the Earth. It'll scatter, it'll sort of move from its direction, get deflected a certain number of times, and then they'll all come out the other side. But once they do come out the other side, they are spread across the Earth's surface like a big cloud of a big cascade or cloud of constituents. And they'll be spread a certain amount of size, which we quantify with this R spread over the Earth's surface. And this depends on a few different parameters. It can depend on the mass of the individual constituents. This sets like how much deflection they will undergo with each scatter. So the more massive something is, if it hits a standard model nucleus, the less it'll deviate from its path. The less if it's less massive, it will deviate with a larger angle. It'll depend on the cross section, because if you have a lot of scatters in the Earth, you're more likely to spread this out, these constituents out over a larger area. And finally, it depends on the entry angle of the dark matter as it comes into the Earth, because that kind of sets the amount of time it spends through the Earth, the length of the trajectory through the Earth. So this also affects the number of scatters in the end. And so I modeled this using a Monte Carlo, essentially, trajectory calculation, where you calculate the mean free path of scattering of each constituent. We modeled like 1,000 of them just to get an idea, and then see where they scattered in the Earth. If they scattered, update their velocity, position, and direction, taking into account the Earth's composition as it goes through the core, mantle, crust, etc. Then once they exit the Earth, you save their exit location, essentially. And you can see how they are spread over the Earth's surface. And taking an average over the entry angle. So we simulate multiple entry angles because, like I said, the amount of spread depends on that. And it depends also whether you go through the core or not, which is a really dense area, so a lot of scattering can occur. And so the idea is, if your detector is in this spread, if it happens to be where these constituents are exiting, you might have a cloud of constituents passing through your detector, and those can scatter multiple times as well. But the key difference to the previous multi-scattering that I was discussing is that instead of one particle scattering all in one line, making a collinear track, you would have a cloud of multiple particles, each of which has a lower cross-section, but because of the higher number of them, you could have multiple scatters, but in different locations based on which of your particles, which of your constituents has scattered. And this can constrain, we can make some constraints or projected exclusions on the single scattering and multi-scattering case. Here, even for constituents that are pretty low mass, low mass comparatively, from like 100 GeV. So this plot has a bit of a lot going on in it, so let me explain. So this line here is the standard single scatter exclusion from the LZ experiment. So if you're looking for a single scattering dark matter like a WIMP, the region to the top/left of this line is where you expect more than one scatter. And so this is excluded by LZ for WIMPs. Now, this teal line that I'm showing you is going to be the region where you expect multiple scatters to occur. And this depends on the number of constituents you had in your initial dark matter clump. So you could have, if you have 10 to the 8 constituents, your density in your final cloud will be higher than if you had 10 to the 6. Thus, this multi-scattering region is eating up more and more of this parameter space. So the key part is that the exclusion for single scatters is now changed, because if your dark matter lives in this loosely bound composite, because it breaks apart and because therefore you might have multiple scatters due to this cloud passing through, that you wouldn't have if it was a single particle passing through with this cross section. You now have to exclude this multi-scattering region from the constraints, essentially. So at high number of constituents, you can have a lot of the parameter space that is getting eaten up by the multi-scattering region, and much of the parameter space could require these multi-scatter searches to be constrained. And this even includes parameter space where the constituents themselves are WIMP scale candidates at WIMP scale cross-sections that you should expect to be constrained by WIMP searches, single scatter searches, except for the fact that they were essentially bound up in these composites. That has enhanced their multi-scattering potential. And you can do some fun other stuff, like for instance, if your constituents are spread over a large enough area, which can happen if they're super more on the lower mass side, you might have 2 detectors in this region. So you maybe could have 2 scatters at multiple detectors in a correlated amount of time. So that would be cool. But what I also want to talk about is not only how can we search for composite dark matter within existing direct detection experiments, which is mostly probed through multi-scattering. We can also use other existing astrophysical objects to broaden the search. The key reason for this is that essentially dark matter that's heavy, as I said, has a very low flux. And so the flux is something like 10 to the 18 GeV per square meter per year. So if you had a detector that was meter squared in area, and you waited for a year, if your dark matter is 10 to the 18 GeV, then you would see 1 particle per year. And that's not great, but you can't really do that much about it. You can only keep your detectors on for so long, and you can only make them so big. So if you really want to push towards the higher mass, like 10 to the 20 GeV and onwards, you should increase your exposure time by looking at objects that are super old or super large, or ideally both. And we can't make those, but they do exist. It's a natural laboratory. So you could look at dark matter affecting stars like the sun, or like white dwarfs, dark matter's effects on galaxies, and dark matter's effects on the Earth itself. And a lot of people have done work on celestial probes of dark matter, astrophysical probes of dark matter in this context. I specifically have worked with my supervisor and collaborators on dark matter inducing type 1a supernova feedback. So I won't go too much into depth into this, but the idea is that if you have heavy dark matter, it can cause white dwarfs to explode when they wouldn't normally. So a white dwarf is held together by electron degeneracy pressure, and generally you're considering that they will detonate into a supernova if they reach a critical mass of the Chandrasekhar mass of 1.4 solar masses. But there are observations of supernovae that are less massive than that. So what could be the cause? One possible cause is that dark matter is captured, passes through the star, interacts, loses energy, eventually gets captured at the core. And that clump of dark matter at the core of the star can collapse and then give off a bunch of energy, and that is enough to set off the explosion. And this specifically could have an impact on a galaxy context, not contest. Because of this key thing called baryonic feedback. Essentially, if you have stellar feedback from supernovae, this is ejecting a bunch of gas, hot, warm gas into the surroundings, and that can reheat the surrounding gas, suppressing star formation. It can cause fluctuations in the gravitational potential of the galaxy and flatten the central density of the galaxy. And cosmological simulations of galaxy evolution have found that baryonic feedback is really key to producing galaxies that are realistic. So normally this baryonic feedback is from normal core collapse supernovae, normal type 1As. But we wanted to look and see what would happen if you put in this extra source of feedback from supernovae caused by super heavy dark matter. So I implemented this in this galaxy simulation called Gizmo. Without going too much into detail, it was essentially calculating how long it would take for white dwarfs of different masses to explode, and then exploding them inside the galaxy simulation. And we found that, as we might expect, dark matter-induced supernovae feedback can suppress star formation. So essentially, the energetics of the initial type 1As, white dwarfs exploding, can eject enough energy into the surrounding gas to kick out the gas from the galaxy completely. So essentially here what I'm showing is a plot of how many supernovae are going off due to dark matter in the left side of the plot over time. The simulation was run for 2.5 gigayears. And on the right side, I have how many how many new stars are being formed in the galaxy. So in the simulation, normally you calculate how many stars are formed based on the temperature and density of the gas. If it's cool enough to start clumping into a star. So if you look at dark matter with really low cross sections, so it takes a really long time to capture inside a star, you don't see a lot of effects on the star formation. As you crank up the cross section of the dark matter, you completely suppress star formation. So in the yellow and green lines, you can see that after it formed that initial step of stellar mass formation, it sort of stops. That's because this has completely blown out the gas and suppressed subsequent stars and subsequent supernovae. So the middle ground is intermediate cross sections, where you slow down the star formation epochs, but you allow enough star formation to then allow more stars to be formed, to then allow more white dwarfs to be formed, to then allow dark matter to explode those as well. And we also found that this can flatten the dark matter density profile. And this was most efficient in those intermediate cross sections because we have the dark matter inducing type 1A effect lasting for longer over multiple star formation periods. So that is essentially the idea. We can simulate galaxies with different dark matters, heavy dark matter masses and cross sections, and see the effects on key aspects of the galaxy, like its density profile and its star formation and therefore luminosity. And the final thing I wanted to touch on briefly is another way to search for super heavy dark matter using ancient minerals. So that's a really large focus of our research group right now. There are many collaborators who unfortunately didn't list on the slide. But the idea essentially is the Earth itself can be a heavy dark matter detector. It's big and it's old. And there are some rocks within the Earth that can be up to 1 billion years old. Hundreds of millions of years to 1 billion years, hanging around and undisturbed mostly. And so if super heavy dark matter passes through, you essentially get like 100 million years of exposure time, which is pretty epic, all things considered. The thing you then have to do is take a look at your mineral and see whether you can see the traces of dark matter having passed through. So the super heavy dark matter that we're considering would pass through a mineral and then deposit enough energy to make a really long, undisturbed track of completely melting the mineral along its path. So passes through, interacts so much that it melts a whole tube of a mineral. And when you melt a mineral and it re-cools, it doesn't, the crystal structure is disturbed. So if you take a look at that crystal structure, you can essentially quantify the amount of defects you get. And so we're doing this using muscovite mica, which is useful for a few reasons. One of which is that it's really easy to slice in parallel sheets, really thin sheets that you can then image using, we're using X-ray fluorescence. And essentially you take the slices like I'm showing on the bottom here. Wish I could point, that's the one thing with Zoom. And if you see when you then image, like you expect your dark matter to make this like angled track. If you then look at your slices and you see coherently like matching blobs on multiple slices, you can infer that that was one thing passing through all those slices at an angle. And that's a signature that has very few or no backgrounds would make, no standard model particles would make a effect of that size that is so extended. So that makes it useful for discriminating against backgrounds. And so with a paper that's coming out soon, we're forecasting some experimental reach using a technique called X-ray fluorescence. And by this, we're planning to extend the dark matter mass experimental detection reach to 10 to the 21, 10 to the 26 GeV in mass, which is pretty exciting. So stay tuned for that on the archive in the coming weeks. Now I will sort of re-summarize everything I touched on today. I know I went pretty fast because there was so much to discuss. The key points were that you can have these heavy composite dark matter clumps forming in the early universe the same way that you have nuclei forming in the early universe with a standard model. Because they have a larger spatial extent, especially if they're loosely bound, they can evade the upper limit on the cross-section that comes from the geometric limit. And so you can have high enough cross-sections to actually scatter multiple times through a detector. And that can be collinearly if it's one particle, or if it's loosely bound enough and it breaks apart into pieces, you could have multiple of these pieces passing through your detector and you can get multiple scatters that way. There's also a lot of ways to search for super heavy dark matter using astrophysical probes, one of which is its impact on type 1e supernova explosion rates. And finally, there's an exciting way to search for dark matter using ancient minerals in the Earth and looking for observable defects. Thank you so much.
Awesome. Thank you so much, Yilda. So for everyone who is joining on the YouTube live stream, if you have any questions, feel free to just put them in the comment section. I will be monitoring the YouTube live stream. And if anyone has any questions inside the Zoom call, feel free to also just put a hand up or anything. I thought I'd start it off myself. So I'm very curious about composite dark matter, as you know, some observations such as the Bullet nebula, or sorry, Bullet galaxy. I think it was the Bullet nebula.
The Bullet cluster, right? Yeah.
Bullet cluster. Sorry, that's what it is now. Yeah. You know, it shows how dark matter and matter kind of interact when you have these clusters collide, and how dark matter doesn't really interact that much with itself. So it does. So most people, you know, would think that dark matter doesn't interact. Does having composite dark matter change that, since that would in fact cause self-interaction?
Right. No, that's a really good question. So yes, you would have a self-interaction due to this attractive force for sure. The thing is, the bullet cluster constrains how much self-interaction there can be. So that can't be very high. So what we're looking at in like this early universe composite assembly is that you have in the early universe, your particles are more and more energetic. As the universe is cooling, their energy drops below a certain point, and then they can start forming these clumps if they're close enough together. But as you keep on going in time, the universe is expanding, so this drops off the interaction rate. Similarly to how in WIMP freeze out, you have an annihilation between dark matter and anti-dark matter. But at some point, the expansion of the universe is overtaking that, and you just don't have interactions at that extent. So for something like a composite state, the interaction, I guess the interaction scale would be small. So in something like the bullet cluster, you wouldn't expect to have sufficient interactions to actually, cause more assembly to form, if that makes sense. But that does set an upper bound on how strong the force between the dark matter particles can be, for sure. That makes sense.
Yes, it does. Thank you so much. Is there anyone else with any questions, either in the Zoom call? I don't see any comments right now in the live stream or on the Zoom call. No, then otherwise I do have one more question.
Sure.
And that has to do with these multi-scatter events that you're talking about. In a lot of dark matter detectors, we have backgrounds that cause multiple scatters, such as muons and such. And so I'm wondering, is there a way to distinguish a multi-scatter from a dark matter composite versus backgrounds?
Yes. I'm not so much on the experimental side, so I have a more basic understanding of the different data selection cuts they would make. Oftentimes, this has to do with the positioning of the scattering. For instance, if you do have one dark matter particle and it is passing through the detector, it's very heavy, and it interacts multiple times all along its track. It doesn't get a lot of deflection from the different scatters because it's so much heavier than a nucleus. So you would see the multiple scatters be very collinear, whereas for a neutron, which is lighter, you might see scatters like bang, 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 like all over from the like miscellaneous way the neutron would move around. So in that case, you could do like a selection cut on how collinear the scatters are. If you're looking at something like the disassembled composites that make that cloud of different constituents that could scatter at a bunch of different places, then it would be a bit harder. And at that time, I think you would have to look at the time delay between different events. And that's something that we briefly looked at, but we didn't compare with a nucleus scattering multiple times and the time delay between those events. So I think you'd have to do some sort of a comparative analysis and simulation of like what the timing between multi-scatters and the energy of multi-scatters for neutron backgrounds versus for something like a multi-scattering dark matter like cloud, if that makes sense. Hello? Oh, Brian, I don't know if maybe I
I
just
think
can't
we
hear
lost
you.
Ryan's audio.
Okay, cool. Sorry if I was talking too long and didn't hear you stop me. I couldn't hear anymore.
Oh yeah, he says his earphones just disconnected.
Okay.
Were there any other questions in the chat? Doesn't look like it.
Sorry, can you guys hear me?
Yep, there you go.
Oh yes, now you can.
Oh, there I am. Yeah, my earphones just died and disconnected right at the end of Yilda's amazing answer. So I was just like, ah. There's no more question. There's no questions on the live stream side of things right now. I think this is a good place to maybe end. But that was a very interesting talk, and thank you for the answering those questions because it's very interesting. Someone who's experimental and specifically looking at WIMPs, what specifically we can do to look for other types of dark matter like composites.
Thank you for having me.
Yeah. All right. Well, this will be on YouTube for forever now. So if anyone ever wants to go and watch this, you can send them that way to have a look at this talk. And yeah, good luck with your PhD defense and everything. I think it's going to go well.